Hey guys, I'm Eric Wheatley, and today I'll be showing you how to do a related rates problem. The problem I chose is exercise 42 out of the textbook, section 4.1. This is the graphic from the textbook, and here's the question itself. A batter hits a ball towards third base at 75 feet per second and runs towards first base at a rate of 24 feet per second. At what rate does the distance between the ball and the batter change when 2 seconds have passed? This is the handout that Professor Seeberger gave us on related rates. I'm going to use this procedure to find a solution to the problem. The first step is to draw and label a picture of the problem situation. I rotated the baseball diamond a bit to make it easier to visualize, and I also changed the name of the axis for the same reason. The ball was hit towards third base, or Y, and the runner is running towards first base, or X. The second step is to identify the variables that are changing as time passes. From the problem, we know that the ball is moving towards third base, or Y, at a rate of 75 feet per second. We can simplify that and say dy dt is equal to 75 feet per second. We also know that the runner is running towards first base, or X, at a rate of 24 feet per second. We can simplify and say dx dt is equal to 24 feet per second. The third step is to rewrite the problem in terms of the rates of change. Our goal is to determine the rate that the distance between the runner and the ball is changing at t is equal to 2 seconds. I will call the value of that rate dr dt. Rewriting now, we can say that we are to find dr dt when dy dt is equal to 75 feet per second, dx dt is equal to 24 feet per second, and t is equal to 2 seconds. The fourth step is to write an equation relating these variables. I have drawn in r, which is the distance between the ball and the runner. We can see that this forms a right triangle, and the best formula that relates our variables would be the Pythagorean theorem. Rewriting it in our variables, we get x squared plus y squared is equal to r squared. The fifth step is to differentiate each side of the equation with respect to time. As we differentiate, x squared becomes 2x times dx dt, y squared becomes 2y times dy dt, and r squared becomes 2r times dr dt. The sixth step is to solve for the desired rate of change. In our equation, we see dr dt, which is the value that we are trying to find. To get dr dt by itself, we will divide both sides of the equation by 2r. The 2's on the left side of the equation cancel, and we are left with dr dt is equal to x times dx dt plus y times dy dt all over r. The seventh and final step is to, where possible, replace the variables, including the rates, in this equation with known values and evaluate to find the value of the desired rate of change. We are given dx dt and dy dt, but we still need to find the values for x, y, and r before we can solve for dr dt. Remember, we were also told to find dr dt at 2 seconds, and that the values of x and y represent the position of the batter and the ball at any time. Using the formula distance is equal to velocity times time, we can find the exact position of the batter and the ball at that 2-second mark, or rather, the values of x and y. Using that formula, we find that x is equal to 48 feet and y is equal to 150 feet. The last variable to find is r, or the distance between x and y at any time. Thinking back to how the batter, the ball, and the distance between them form a right triangle, we can find the distance between them, or r, at 2 seconds using the Pythagorean theorem. By plugging in our values for x and y, we find that r is equal to 157.493 feet. We now have all of our variables needed to solve for dr dt. Plugging our values into the formula for dr dt, we see that dr dt is equal to 78.75 feet per second. Putting it back into the context of the problem, we can say that 2 seconds after the batter hit the ball, the distance between the batter and the ball is increasing at a rate of 78.75 feet per second. Thanks for listening to me, guys. I look forward to watching all your videos.